We present a novel autoregression network to generate movements for virtual agents that convey various emotions through their walking gaits. Virtual agents are often used as avatars in social AR and VR environments. Apart from looking realistic, we also require the virtual agents to be able to express different emotions to increase their sense of social presence. We focus on designing virtual agents that are capable of expressing different emotions through their gaits. To summarize our main contributions, we present an autoregression network that takes in 3D poses of a VA's gait, a desired trajectory, and the desired emotion. It outputs the VA's gait expressing the given emotion and following the given trajectory. We formulate a novel training method that combines movement features and psychologically motivated affective features into a unified network that can generate plausible, emotionally expressive gaits for VAs at interactive rates. We also integrate the VAs with these generated gaits in an AR environment. We conduct a web-based user study where observers reported perceived emotions from the generated gaits and the perceived values of the affective features. We perform statistical tests on the results of the user study to verify the emotional expressiveness and the naturalness of the gaits, and observe how the emotional expressiveness of the VAs adds to their social presence. To achieve emotional expressiveness, we encode gait-based affective features into our network. Our affective features are made of 11 joint angles, 4 distance ratios between pairs of joints, and 3 triangle area ratios between triplets of joints. In order to make the gaits follow user-driven trajectories, we also encode gait-based movement features into our network. Our movement features include the root height from the ground, the root speed between time steps, and the phase of the feet between the points where they touch the ground. We also include features like root orientation relative to the tangent to the trajectory curvature, and the frequency of footsteps. Now we present an overview of our sequence prediction network. It consists of 2 main components, the encoder followed by the predictor. The encoder takes in the joint positions and rotations of the input gait for a number of time steps and extracts pose affective features and root joint features from the input gaits. Next, it learns the encoding functions to jointly map these extracted features, the corresponding input emotions, and the movement features to latent representations. It achieves this by using fully connected layers to map all the input features to hidden variables, followed by a GRU to combine the joint rotations with the hidden variables and encode them to latent representation. The predictor learns to compute the inverse mapping from the latent representations to the necessary affective and trajectory features and, by extension, joint positions and rotations in the subsequent time steps. It achieves this by passing the latent representations through different sets of fully connected layers and normalizing the rotation outputs so that they represent valid versors. We evaluate the performance of our method on gait datasets collected from multiple sources. We show a few qualitative results. Here we show 4 VA gaits expressing the 4 emotions: happy, sad, angry, and neutral. The VAs walk on user-driven trajectories marked with the red line. Next, we show transition of emotions in the gaits. In this video, the VA first transitions from angry to sad. We can see the VA slowing down and its shoulders slouching as the emotion transitions to sad. The VA then transitions from sad to neutral. The shoulders become less slouched. Finally, the VA transitions from neutral to happy. It begins to move faster and finally breaks into a jog. We also compare our motion generation with the state-of-the-art network of Pavlo et al. As we can see, their network cannot perform emotional expressiveness. We also show comparisons with ablated versions of our network. First, we remove only the affective feature encoding and constraints from our network and train the remaining network. As we can see, this network cannot generate the different emotional expressions. Next, we remove only the movement feature encoding and constraints from our network and train the remaining network. This network can generate different emotional expressions, but is unable to follow user-driven trajectories. We now show some generated emotive gait samples in the AR environment. We first use stick figures to depict VAs. Stick figures have the advantage of abstracting away irrelevant features of the VA, such as facial expressions and attire. We show gaits in pairs so the observer can more easily understand the differences in expression for the different emotions. For the sake of completeness, we also use human models to depict the VAs. We again show the gaits in pairs and use a female and a male model in each pair. To summarize, we have presented here a novel autoregression method to generate emotive gaits moving along user-driven trajectories. This is the end of our presentation. Thank you for listening.